Okay, so this is the term for a single nucleon, right? This is the Hamiltonian we have written. And so now the final for all the nucleons, I can write the final wave function phi mu as an antisymmetric product of a single particle states. This psi k, single particle states. Now you must remember in your atomic molecular class you have done something like this, right? So this phi mu is written as a Slater determinant. Fine. Now what about this Ek? So this, remember the epsilon mu, this is equal to summation over k Ek, and the sum is over the occupied states. Fine. Now what next? So remember we started with this H psi equal to E psi. Later on I separated it, okay, and I introduced new basis states, this phi for them, okay. So after that, what the entire system looks like? The entire system now looks like this. So summation is over there everywhere, right? I'm just taking the important part. Now look, if the system is diagonal in H0, there is no H1 present, then only this will be here. But what is H1 doing? The presence of H1, residual interaction. The presence of H1 means that now this phi will no longer be the entire system's wave function. Is it true or not? Actually, you see, the presence of this H1 will cause these phi's to mix among themselves. Look over here. Now, what's a configuration? A configuration is basically an arrangement of A nucleons. So, each arrangement of A nucleons is represented by this wave function psi. Good. Now, because of this presence of H1, what is happening is that all this psi we have written, this we have introduced, right? Now because of this H1, you can see if there is no H1, this is good enough, no mixing. But because of this there will be a linear combination of basis states, and so the final nuclear wave function psi, it has to be written as a linear combination of these basis states. And so this means there is a mixing between these basis states phi, and this is known as configuration mixing. Remember, there is nothing very unusual or very hard about it. Configuration mixing means that this term is present. Since this term is present, so all the wave functions, this phi, they will be mixed among themselves. That's all, nothing else. And so the final wave function will just be a linear combination of these phi wave functions. And this is known as, referred to as configuration mixing. So if I ask you in the examination, what is basically configuration mixing and why does it happen? So what will you say? The reason is due to residual interaction. And why is there residual interaction? Because it is impossible to erase the effect of 3 body and more interactions, right? We just cannot do that. That means in the entire nucleon interaction in the nucleus, mean field cannot be the only one who is responsible for all the interactions. There are forces beyond mean field. Okay, So beyond mean field forces are present and residual interaction is a manifestation of it. Now you will see that when I will show you the experimental predictions for, say, the case when there is no configuration mixing, you will see that the theory and experiment don't match. And if you do configuration mixing, they do match. What's the meaning of this? The very fact that that theoretical predictions match with experimental results for the case of configuration mixing means that residual interaction is present. And also it means that it is not very much. Otherwise we have to do a complete diagonalization. Okay? To write this down, whatever I have mentioned. In your own language, write it, okay? Okay, so you see, this H mu nu, you remember, I write it down just a few boards backward. That is basically an infinite dimension. Now in theory, it seems okay to write down infinite dimension. But this means that there are infinite configurations leading to an infinite dimensional Hilbert space. So how are you going to solve it? What should we do? So now we will introduce truncations. So what is the meaning of truncation? The meaning of truncation is, think of it like that. We have got a system, right? Now, what is the property we are going to try to understand from this system? Now, it so happens that the major part of the system, this one, this is not required to, it doesn't contribute to that property. Then what will we do? We just ignore it, right? So truncation means to just forget about it, ignore those parts, and this is the only one that we will be considering. Now look what has happened. Previously it was such a large, try to think it like that, such a large problem. But now I have ignored most of it. Truncation, I am just considering a part of it. Students also do something like that. Say for example, after a few weeks, you will ask me, sir, what questions will come in the examination? Okay? Now see, truncation. I will say, number 1, no last year question. Truncation. So this way, if you have a set of questions, no last year questions means this is okay, you don't have to do this. Good. Next I will say, okay, this part is hard. So suppose I am not going to ask you from this part. So again, more truncations. So on and so forth. So you see, now you have to study this part only. This we all the time do. In class 10 exam, class 12 exam, suggestion. What's the suggestion? Ki asche. So basically it's truncation. We are trying to reduce our load. We are very lazy people, you see. All the time we are doing this, truncation. A physicist is just like that. So, truncation. Now, as I was saying, the most basic truncation is what? Remember, we have got this. H is equal to H0 plus H1, right? So the most basic truncation is ignore this part so that only H0 remains. And this means now in the system only H0 is there, and this is known as independent particle picture. Or you can also say independent particle shell model. So when you say independent particle shell model, this means all the other parts which are dependent, they have been ignored. And this is the part we have ignored. Okay? So all the other residual interactions are absent in the system. This is very important. See? Approximation. Slowly we will move forward. Now next thing, you have already done that in your graduation. In your graduation class, have you ever considered the effect of this residual interaction? Never. You have just considered this H0. You use harmonic oscillator potential or Wood section potential plus L dot S interaction plus L square term, right? What about the other interactions? You never considered it. So in a way, in your entire graduation, even in your school, you have considered this independent particle picture. This is what you have done. Now what I have done today is I have started with the general formalism and shown you that look, this is what you have done. And slowly and gradually later on, I am going to see the effect of this later on. Okay, so this is for the later term. Right now, consider this independent particle picture. Any more questions? So, at the end of such a long class, we are back to square one. So, this is where you all started. But remember the difference. Today we started with the most general case possible, and then I showed you that why you have done what you have done. Why you have just considered this independent particle picture in your graduation and not the entire general term. Because it is very difficult to treat. In your graduation or school days, you never knew the mathematical tools to deal with this H1. But now you know. So, since you have done that, I will now concentrate on this H1. So, this is the aim of this course, that I am not going to talk about the effects of this independent particle picture, but on the H1. What are the after effects of this H1? The presence, right? These for questions?
তাহলে এটা বলতে পারি যে UI পোটেনশিয়ালটার জন্যই আমি ট্রান্সলেশনটা করতে পারছি।
Choice, right? If I use a different UI which is not good enough, H1 will be there. So see, independent particle picture, this you have considered in your graduation or even in school days. So we consider the harmonic oscillator part, the L dot S part and the L dot A or L square interaction. What are the coefficients over here? Number 1, number 2, number 3. And you must remember that by tuning these coefficients, we are able to reproduce the magic nuclei, magic numbers, also ground state spin parity of most ground state, right? Not the excited state. Of most odd nuclei, we are able to reproduce. What about excited states? Why not? You will see in your graduation book there is no mention of that. They don't talk about. The reason is that simple. Independent particle picture is unable to deal with the excited state. Their residual interaction effects will be there. Okay? Write it down. This is why in your graduation book there was no such mention.
Sir?
Yes?
যদি এক্সাইটেড স্টেট আমার কাছে জানা থাকে আমি ওর সাপেক্ষে কোনো একটা পোটেনশিয়াল UI ইউজ করে আমার অপটিমাল রেসিডিউটা আমি জিরো করতে পারছি।
Okay, so your question is, suppose I have got excited state, if I can tune particularly to make this excited state, then this will not match. And you don't have to consider only this nuclei, you have to consider all the neighboring nuclei as well. When you tune V0 alpha beta, you are tuning all of them together. You will see it is not possible to just do this, consider the excited state. The tuning will not be good enough. Excitation কিভাবে করা হবে? নিউক্লিয়ার তুমি যদি কোনো সিস্টেমকে এক্সাইটেড এনার্জি দেবে, if you excite the nucleus will hop on. So if we consider a basic shell model, Let me talk about the independent particle picture now. Shell model, right? So ground state, what is it? The shell model picture. Tell me. Shell model. This is the shell model orbit.
One is half.
Okay.
150 by
1p
3 by 2.
3 by 2. 1p half.
2 half.
Next.
2 is half.
Yes. No. 1 to 5 by 5.
1p 5 by 2. Next.
2 is half.
2 is half. Next.
1 to 3 by 2.
1d 3 by 2. Okay. Good. Now you see, just now I have mentioned that most ordered nuclei, right? And also ground state. Now let us try to deviate from it, move away from it. So most ordered nuclei, ground state. This independent particle pictures one of the greatest success story. Now let's move away from it. Suppose, let me consider the case of 18 oxygen. 18 oxygen. So what is it? You can think of it as 16 oxygen plus 2 neutrons. This is not an ordered nuclei. This is an even nuclei. Good. So 18 oxygen. So oxygen means 8. Right? So number of protons 8, number of neutrons 10, here 8. Now let me first write down what the picture of 18 oxygen, 16 oxygen. So this is 2. Now in the case of 16 oxygen, if this is neutron and this is the case for proton. Remember I am talking about independent particle picture. So this is for neutron, this is for proton. Again, let me use different symbols for protons. How many? 2j plus half. So 2 into 3 by 2 plus half, 4. Here again 2. Here again 2. And this is your 16 oxygen. Okay, this is your 16 oxygen. Good. So for 18 oxygen, there will be 2 neutrons over here. No change for the case of protons. So let me rub this part. Now, next thing. What is the possible angular momentum due to these 2 nucleons in 1d fiber? What will it be? Angular momentum possible? You write it down. J plus J, vector sum. So 5 by 2 plus 5 by 2 vector sum. So this means 0, 1, 2, 3, 4 and 5. Right? Is this correct? Why and why not? When I am doing the vector sum, this is okay. 0 to 5. But consider the fact that this we are talking about 2 neutrons. What are they? Fermions. Pauli's exclusion principle will be valid. No 2 fermions with the same quantum number. But I have not said anything about it like this. So what is happening actually here? Some of them are for bosons and some of them are for fermions. That means some of this angular momentum will correspond to symmetric state and some correspond to antisymmetric state. Now we have to find out it. Which one corresponds to fermions or antisymmetric state? This is what we have to do. Okay? And for that we have to I will introduce this very unique technique known as M scheme. Using this, we will be able to understand which angular momenta correspond to states that are antisymmetric. Any questions till now?
স্যার এটা আরেকবার বলে দিন শেষটা।
বলো। আমি বলছি, what I am saying is that this sum integral, half integral, this is okay, but this is an integral value. So some of them will correspond to symmetric states, some to antisymmetric states. And just by using this M scheme, we will be able to get rid of this.